Hello, welcome. In this lecture, we show how the ideas of tangent and normal vectors and curvature can be used in physics to study motion of an object, including velocity and acceleration along a space curve. Suppose a particle moves through space so that its position vector at time t is r of t. Notice from the figure that for small values of h, the vector in equation 7.1.1 approximates the direction of the particle moving along the curve r of t. Its magnitude measures the size of the displacement vector per unit time. The vector in equation 7.1.1 gives the average velocity over a time interval of length h, and its limit is the velocity vector v at time t. Shown in equation 7.1.2. Thus, the velocity vector is also the tangent vector and points in the direction of the tangent line. The speed of the particle at time t is the magnitude of the velocity vector. That is, the magnitude of the vector v. This is appropriate because from equation 7.1.2 and from equation 5.1.4 from the lecture 5 part 1, we have the velocity vector is equal to the magnitude of the derivative of the position vector, which is equal to the derivative of the arc length function with respect to time, or the rate of change of distance with respect to time. As in the case of one-dimensional motion, the acceleration of the particle is defined as the derivative of the velocity. Consequently, it is the second-order derivative of the position vector. Let's consider an example. The position vector of an object moving in a plane is given by the following vector function, whose first component is t cubed and the second component is t squared. Find its velocity, speed, and acceleration at t equals 1. Let's see the solution. The first and second order derivatives of the position vector r give the velocity and acceleration vectors of the particle at a time t, respectively. Therefore, the velocity vector is the first derivative of the position vector, whose components are 3t squared and 2t. Similarly, the acceleration of the particle at time t is given by the second derivative of the position vector, or the first derivative of the velocity vector. Therefore, it has the components 6t and 2. And the speed of the particle at time t is given by the magnitude of the velocity vector, which is the positive square root of the sum of the squares of the component of the velocity vector. Therefore, at t equals 1, the velocity, acceleration, and the speed are given by the following quantities. V at 1 equals 3i plus 2j. It is obtained by simply substituting t equals 1 into the velocity vector function. Similarly, the acceleration at 1 is the vector 6i plus 2j. And the magnitude of the velocity at t equals 1 is the positive square root of the sum of the squares of its components, which simplifies to positive square root of 13. In general, vector integrals allow us to recover velocity when acceleration is known and position when velocity is known. Let's see an example. A moving particle starts at an initial position, r at 0 is the vector with components 1, 0, 0. With initial velocity, the vector with components 1, negative 1, 1. Its acceleration is given by the vector with components 4t, 6t, 1. Find its velocity and position at time t. Let's have a look at the solution to this problem. Integrating the acceleration vector with respect to time, we obtain the velocity vector. So the vector has components 2t squared, 3t squared, t, plus a constant vector c1 of integration. To determine the constant vector c1, we apply the initial velocity. V at 0 is the vector with components 1, negative 1, 1. Therefore, substituting t equals 0 into the equation 1, in the left hand side we obtain v at 0, which would be eventually replaced by this vector. And in the right hand side we have 0, 0, 0 obtained from here, plus the constant vector c1. Now solving this equation for the constant vector c1, we obtain the vector 1, negative 1, 1. Therefore, the velocity vector is given by the equation 2. Now integrating the velocity vector with respect to time, we obtain the position vector of the moving particle with the components shown here. Where c2 is an arbitrary constant vector. Similarly, to determine the constant vector c2, we apply the initial position r at 0 is a vector with components 1, 0, 0. And this gives the constant vector c2 as the vector with components 1, 0, 0. Therefore, the position vector is given by the vector with components shown here. The problem is now completely solved. If the force that acts on a particle is known, then the acceleration can be found from Newton's second law of motion. The vector version of this law states that if at any time t, a force f of t acts on an object of mass m, producing an acceleration given by the vector function a, then f of t equals to m times a of t. Let's see an example. An object with mass m that moves in a circular path with constant angular speed omega has a position vector described by this vector function. R of t equals a times cosine of omega t I plus a times sine of omega t j. Find the force acting on the object and show that it is directed toward the origin. Let's have a look at the solution. Let's first differentiate the position vector r with respect to time to obtain the velocity vector, which is given by this expression. Negative a omega sine of omega t I plus a omega times cosine of omega t j. And if we differentiate this vector again with respect to time, we obtain the acceleration vector, whose components are shown here. And it can also be written by factoring out omega squared. So the acceleration becomes negative omega squared times the position vector. Therefore, by the Newton's second law of motion, the force acting on the object is given by the mass times the acceleration, which becomes a vector with these components. Can also be written as negative m times omega squared times the position vector of the particle. The last equation here shows that the force is parallel to the position vector, since it's a constant multiple of the position vector, but acting in the opposite direction to the position vector. Hence, it is directed toward the origin, as shown in the following figure. When we study the motion of a particle, it is often useful to resolve the acceleration into two components. One in the direction of the tangent, and the other in the direction of the normal vector. If we rewrite the speed of a particle as v, then the tangent vector, which is given by the ratio of the vector r prime over its magnitude, which can also be written in this way, and by writing the speed v as the magnitude of the velocity vector, we obtain this expression. Therefore, the velocity of the particle is equal to the speed times the tangent vector. If we differentiate both sides of this equation with respect to t, in the left-hand side we obtain v prime, which is the acceleration, and in the right-hand side we apply the product rule for differentiation of vector, which is the product of scalar function with a vector function t, as shown in equation 7.1.3. Now, if we use the expression for the curvature given in equation 5.2 2.2. Then we have the curvature equals to the ratio of the magnitude of the derivative of unit tangent vector over the magnitude of the first derivative of the position vector, which can also be written as v. Therefore, the magnitude of the first derivative of the unit tangent vector can be written as the product of the curvature and the speed of the particle. The unit normal vector was defined in the preceding section as shown. So the equation 7.1.3 gives the acceleration equals to the derivative of the speed times the tangent vector plus the speed times the magnitude of the first derivative of the unit tangent vector times the unit normal. Now substituting the expression kappa times v for the magnitude of the derivative of unit tangent vector, we obtain equation 7.1.4. Writing a sub t and a sub n for the tangential and normal components of acceleration, we have the vector a can be written as the sum of these two vectors, a sub t times the unit tangent vector and a sub n times the unit normal vector, where a sub t is the quantity v prime and the a sub n is the quantity kappa v squared. The tangential and the normal component are shown in this figure. Although we have expressions for the tangential and normal components of acceleration in equation 7.1.4, it's desirable to have expressions that depend on the position vector and its first derivative and its second derivative. To this end, we take the dot product of the vector A with the tangent vector as given by equation 7.1.5. By using the property that the unit tangent vector has magnitude 1, so is the unit normal vector, we have the component a sub t equals a dot the unit tangent vector. So if we take the dot product of a with the t, we have a sub t times t dot t plus a sub n t dot n. This is the magnitude squared of the unit tangent vector, which is 1, and t dot n is 0, since the unit tangent vector is orthogonal to the unit normal vector. So we have a sub t, the tangential component of the acceleration, equals to a dot t. Similarly, the normal component of the acceleration is given by a dot the unit normal vector. Now, from this equation, a dot t is A dot v over v, which is the magnitude of the velocity vector. So A dot v is in fact the dot product of r double prime dot r prime, which is written here. So we get the expression for the tangential component. Similarly, with the expression for the curvature kappa that is given in theorem 5.2.1 in lecture 5 part 2, we can write a sub n equals kappa v squared, and this expression is the kappa, and this is the v squared. So if you simplify, we get the normal component of the acceleration as shown in the last equation. Let's see an example. A particle moves with position vector given by the vector with components t squared, comma, t squared, comma, t cubed. Find the tangential and normal components of acceleration. Let's have a look at the solution of this problem. To calculate the tangential and normal component of the acceleration vector, we first calculate the acceleration vector. So we first compute the velocity vector r prime, whose components are 2t, 2t, 3t squared. From there, we can compute the r double prime, which is the second order derivative of the position vector r, whose components are 2, 2, 6t. And then by using the expressions we obtained in the previous page for the tangential and normal components of the acceleration vector, we use these expressions. Warning: do not simplify the expressions for the tangential component and the normal components in the following way. What's wrong with these simplifications?